Okay, so in this video we're going to talk about stellar evolution, and we've talked about a little of this before, but basically stars start out as giant dust clouds, right? Just, nebulae. And so what happens if you have a nebula filled with gas and dust is over time, gravity can pull those dust and gas particles together. Now, most of those gas clouds are going to be hydrogen. Of all of the mass in the universe, about 75% of the mass is hydrogen, and so it's mostly going to be hydrogen. And gravity is going to act between those gas particles and pull them together over long periods of time. Now, as they pull together, they're basically losing gravitational potential energy, but gaining kinetic energy, and so they're going to fall towards each other faster and faster and faster. And as that happens, the temperature of the cloud of dust is going to increase over time, and eventually, if there is enough gas particles, if there's enough mass in the cloud, then the gravitational pressure acting inward is going to create enough kinetic energy to create fusion. Now, at this point, this is not a fully formed star. This is just what you might call like a protostar. Protostar is still very large, might be really hot. But once the fusion starts is when the exciting stuff happens. And so on this slide in the notes you can read what it says, but it says as the gravitational contraction continues, the temperature of the core of the protostar continues to rise until it is at a sufficiently high temperature for all the electrons to be stripped from their atoms, making up the core. In other words, the electrons or those atoms become ionized. And now you have a plasma, and what do you get when you have a plasma and you have really high temperatures and high pressures? You can get nuclear fusion, and we've talked about that before. And typically in nuclear fusion, what you're talking about is converting hydrogen into helium. Hydrogen can fuse into helium if you have enough energy, and then you have a main sequence star. Now remember, what makes a main sequence star is that it's fusing hydrogen into helium. And that's where star is going to spend most of its life, is as a main sequence star, just fusing hydrogen into helium. And of course, when that happens, you have some type of what they call hydrostatic equilibrium, or you have a balance between the inward gravitational pressure caused by all that mass trying to pull itself together and the radiation pressure created by nuclear fusion, because that produces a lot of heat acting outward. And there's some type of equilibrium between that in a normal star. And so on the next slide, you can see how, you start as a protostar and eventually you go plop and you end up somewhere on the main sequence. Where you end up on the main sequence depends on how much mass the star had to begin with, the protostar had to begin with. And of course, that depends on the size of the dust cloud that it was formed from. So obviously, bigger stars would, or bigger dust clouds would have probably end up higher up on the main sequence because they would be bigger and hotter, and so they would be more luminous. Our sun, of course, is kind of in the middle of the main sequence right here. And this slide is basically saying what I just said. Where a protostar lands on the main sequence is determined by its initial mass. The greater the initial mass, the higher the final surface temperature, and the greater the luminosity is going to be. Because obviously, if a star is hotter, it's more luminous, and if it's bigger in size, it's more luminous. We know there's a relationship between mass and luminosity from the last video. And so bigger stars tend to end up higher up on the main sequence just because they have more mass, and so they're hotter and more luminous. Okay, now we have talked about before, just briefly, that the bigger a star is, number one, the bigger a star is, the faster it ends up on the main sequence, just because there's more mass, it's able to pull itself together more quickly. But also, the bigger stars have shorter lifetimes because they have so much mass, there's so much gravitational pressure inside the star, the rate of fusion is much higher, and so bigger stars tend to die out faster than smaller stars. And so on this graph you can see these times shown in this picture is not how long the star is going to live, but basically how long it takes to go from that protostar, that that nebula of gas and dust into a main sequence star. And you can see, a couple thousand, tens of thousands of years for the biggest stars, and then smaller stars take much longer to end up on the main sequence. And then once they're on the main sequence, they also last longer because the rate of fusion is much less. Now, you should also know that there are upper and lower limits on the mass of matter that can form a star. So basically, if you don't have enough mass to form a star, then what's going to happen is the mass is going to pull itself together, right? But there's not going to be enough heat produced by the gravitational pressure to initiate fusion. And then you have what's called a brown dwarf. Now, a brown dwarf, I believe, is 10 or 20 or 30 times the mass of Jupiter. And so Jupiter, if it was, let's say, 30 times more massive than it is, could have actually formed into another star, but it didn't have quite enough mass. I might be a little bit off on those numbers, but brown dwarfs are basically failed stars. They're stars that would have formed, but they didn't have enough mass to produce the heat necessary to cause fusion. And so there's a lower limit on how big a star can be. Now, there's also an upper limit on how big a star can be, because if you have too much mass, then when the star is trying to form, there's a lot of internal pressure that's disrupting the evolution of the star if there's too much mass trying to pull itself together. And so there's both an upper and a lower limit on the mass of a star. Now, we've talked about how being a main sequence star means the star is fusing hydrogen into helium. Now, eventually what's going to happen in the core of the star is all the hydrogen is going to be gone, and you're going to be left with just helium. Okay, now, of course, we talked about before how long that takes depends on the star's mass, because a bigger star is going to burn faster. Our sun has been converting hydrogen into helium for billions of years. A star more massive than our sun might only take, a couple million years to reach the same point in its evolution where our sun currently is. Now, just to gauge where our sun currently is, this is kind of a little timeline showing you our sun. Of course, this is only roughly approximately correct, but you can see our sun was born over here, and we're currently about 4.5 billion years into our sun's life cycle. And our sun is a main sequence star, and it's been a main sequence star basically all of its life. Now, over the next couple billion years, what's going to happen, and we'll talk about this process here in a minute, is our sun is going to gradually warm and eventually grow into what's called a red giant. That red giant is eventually going to release what's called a planetary nebula and leave behind the core, which is what we call a white dwarf. And we'll go into that in more detail, but this is going to be the life cycle of our sun. Our sun is eventually, billions of years from now, going to end up as a white dwarf. Okay, now, how does that happen? Well, basically what happens is when a star is done being a main sequence star, that means all the hydrogen in the core has been used up. That means fusion just stops because you have no more hydrogen left in the core. And so what's going to happen now is at that point, remember, in a stable star you have an equilibrium between gravity pulling everything in and the radiation pressure from fusion pushing everything out. And so fusion stops in the core is going to contract. Okay, because gravity basically wins at that point. Now, when I say hydrogen in the core has been used up, that doesn't mean there's no more hydrogen left in the star. That just means there's no hydrogen left in the core of the star. There's still hydrogen in the outer layers. And so what's going to happen is the core is going to contract because of gravity, and as it contracts, it's going to become hotter, and that's going to release more energy, and that energy is going to ignite the outer layers and cause fusion to occur in the outer layers of the star. And so basically the fusion process is going to kind of re-jumpstart itself. Okay, but at this point now you're basically done fusing the core of the star. That's just completely helium now, and now you're starting to fuse the hydrogen that's surrounding the core. Now, as the core contracts, of course, I said before, it's going to produce more heat because that's what happens when you compress things. It generates more heat and more energy. It's going to cause the it's going to cause the sun as a whole to expand because of all that extra heat. Now, what's going to happen is as the surface of the sun expands, the overall temperature of the sun is actually going to drop, but its luminosity is going to increase. Now you might ask, well, if it's getting colder, number one, you might ask, how is it getting colder? Number two, you might ask, well, if it's getting colder, then why would the luminosity increase? And the answer to the first question is the surface temperature is going to drop because if you take a star and you expand it, we know just from last year talking about thermal physics that if you think of an ideal gas, if you have if you increase the volume of a gas and keep everything else constant, I was going to say the temperature going to increase, but that's not correct. Let me rephrase that. If you sorry, what I meant to say is if you take a star and increase its volume with the same power output, then what's going to happen is the overall energy is spread out over a wider surface area, and so the temperature is going to drop. Now, the luminosity is going to increase because even though luminosity does depend on temperature, it also depends on size. Okay, and so if you make the star much, much bigger, even if it does cool down, the overall luminosity is still going to increase. And then you get what's called a red giant. Okay, the surface temperature is going to go down, of course. The radius is going to be much, much bigger than it currently is, which is bad for us on the Earth because it might even expand and swallow the Earth. Okay, here you can kind of see how the Earth is going to expand, possibly out past the orbit of Mars. I'm not sure if we accurately know exactly how far the Sun is going to expand when it enters its red giant phase, but it is entirely plausible that where the Earth currently is might be swallowed by the Sun when it becomes a red giant. Okay. Luckily, that's not going to be for billions of years, and so that's not something we have to worry about. Now, on this slide, you can read what it says here, but basically, it's still talking about the whole red giant phase. Okay, so core contracts, creates more heat, starts burning hydrogen on the outer shell of the star, and then what can happen is if you have enough mass, the core can contract again, create more heat, and if it gets hot enough, it can even cause helium to fuse. Now, typically when you talk about nuclear fusion, you're talking about hydrogen fusing into helium, but if you have high enough temperatures, you can also fuse helium into higher elements like carbon or oxygen. And so, depending on the mass of the star, the whole red giant thing can actually happen in phases. Okay, because you can produce heavier elements inside the core of a star as long as you have high enough temperatures. And so if you have high enough temperatures, you can fuse carbon and oxygen all the way up to iron, I believe, depending on how much mass the star has. Okay. And what's going to happen next is basically the Sun is going to reach the point where it's become so massive that the outer layers of the Sun, which is now a red giant, basically kind of get dispersed off into space. And this is what we call a planetary nebula. You can see what it says in the second bullet point. In this process, the core will be exposed. Because of its surface temperature, the energy emitted will ionize the outer gas layers, causing them to emit visible radiation, producing a planetary nebula. Okay, and so this planetary nebula is basically the outer shells of the red giant that's expanded so much, kind of bursting off into space. Not the same as a supernova. You might have heard of a supernova before. This is a different process. This is much less exciting. They're just going to kind of poof off into space. Now, when that happens is most of the mass of the Sun is going to disperse off into the planetary nebula. And in the planetary nebula, what can eventually happen is gravity can pull the planetary nebula back together and create more fusion, and maybe you can get a different star, a new star. Now, when the planetary nebula goes off into space, the core of the star remains. Okay, the radius of the core of the star at this point is about the size of the Earth. Okay, no more fusion is happening because we've run out of fusible mass at that point. And so we have what's called a white dwarf. What we call a white dwarf star is basically just the core of the star after the planetary nebula poofs off into space. And so you get the red giant, the outer shell of the red giant kind of drifts off into space at the end of its lifetime, leaving behind the core of the star, and that core is called a white dwarf. Okay, now a white dwarf is very, very hot, which is why it's white, but it's also very small, and so it has a very low luminosity because its size is only about the size of Earth. Now keep in mind that a white dwarf star, there's no more fusion happening because, well, otherwise it wouldn't be a white dwarf star. And so this white dwarf star is no longer producing any new energy. It's just out there, it's really hot, but eventually, left to its own devices, it's just going to cool down. Over trillions and trillions of years, it's going to become what's called a black dwarf. Now, a black dwarf, no black dwarfs actually exist because the time to become a black dwarf is way, way longer than the current age of the universe. But theoretically, when you get to a white dwarf star, because there's no new energy being produced, eventually it's just going to cool down and become a black dwarf. Okay. Now again, that's not going to happen for a very long time. You would have to, take the age of the universe and multiply it by 1,000. In order to have enough time for a white dwarf to turn into a black dwarf. So, but that's very long-term type of thing. Now, everything we've talked about to this point is only true for stars up to a mass of about 8 solar masses. Okay, and so the processes I've described are only true for a star that's relatively low mass. Okay, so just to review, evolution of a star of a mass under 8 solar masses. These are relatively small stars. The evolution of a low mass star stops when the core is mainly runs out of helium or carbon or oxygen or neon or magnesium, whatever it is that's fusioning in the core of the star. Now, it's very possible that the star manages to fuse hydrogen into helium, but it doesn't have enough mass to keep going after that. It's also possible that the star has enough mass to compress again and fuse that helium into carbon and oxygen, but it all kind of depends on the initial mass of the star. But eventually it's going to run out of fuel. And when that happens, we know that, it's going to become a red giant. The outer layers are going to be forced off into space to produce what's called a planetary nebula, leaving behind the exposed core of the star, that is the white dwarf. And so here is basically the end result of a red giant. You can see there in the middle, that tiny little dot is the white dwarf that's eventually going to cool down. And this outer layer here is what we call the planetary nebula. Okay. And so let me just show you a quick clip of a red giant at the end of its lifetime. Of course, this is just an animation. This is not realistic. This was a computer simulation. So we can see the star is expanding. It's a red giant. Okay, it gets to the point where it's going to start shedding its outer layer into space. And now the red giant is approaching the end of its lifetime. By the way, just to pause it really quickly, once it gets to this point, this process can happen over thousands or even millions of years, which is very short on the scale of a star. Okay, so this happens relatively quickly once it gets past the red giant phase. We can see, poof, that outer shell of the red giant goes off into space, leaving behind the core of the star, that white dwarf, and then this is the shell that just kind of poofed off into space. This is the planetary nebula. Okay, now I know it kind of looked like an explosion, but it's really not. Again, if you've heard of a supernova, this is not the same thing as a supernova. Supernova only applies to stars that are much more massive, greater than the 8 solar masses that we talked about before. Okay, so there, again, that red giant poofs, the shell becomes the planetary nebula, and the core remains behind. No more fusion happening, just basically a hot piece of dead star. Okay, still white hot because it's been, basically burning and producing energy for billions of years, but now it's going to cool down and over trillions of years eventually become a black dwarf. Okay, and so I think most of this we've covered before. Obviously, white dwarfs are small and white in color. They're very hot, but they're also very small because of their size, so they have a low luminosity, and eventually a white dwarf will turn into a black dwarf. Okay, none currently exist right now because, again, it would take trillions of years for that to happen, if not more. And the universe is only about 14 billion years old. All right, so that is basically the evolution of stars that have low mass. Now, on this chart, we can see that basically we've talked about the first 1, 2, 3 rows on this chart. Okay, this is showing what happens if you have a star with a mass less than 0.25 solar masses, all the way up to 8 solar masses. Now, in all cases, at least those first 3 cases, you get fusion happens, and eventually fusion stops, and at the end of the day, you end up with some type of white dwarf. Now, what happens if you have a star that has a mass more than 8 solar masses? Well, at that point, you don't get the white dwarf outcome anymore. Okay, something completely different is going to happen, and we'll talk about that in the next video. But we've only basically just scratched the surface as far as stellar evolution goes. Okay, so what we've just described applies to our sun, but does not apply to the more massive stars. Okay. And this basically shows you the summary of those stars, with a mass less than 8 solar masses. Can you kind of see how this summary goes, ending up with a white dwarf and a planetary nebula. Okay, now what we're not going to talk about quite yet is we're not going to talk about what if you have a more massive star, and it turns out there's actually a limit to how big a white dwarf can end up. We will talk about that in the next video, and then we'll also talk in the next video about what happens if you have a star with a mass greater than 8 solar masses. It goes through a different process and actually has a much more exciting ending than just ending up as a white dwarf. So, as always, please let me know if you have any questions. I hope you enjoyed the video. Just let me leave you on one more thing. This is mainly for more massive stars, but you can see that when a star goes through its red giant phase, it can end up with different layers of different elements because these different elements can undergo different stages of fusion. Now, in the stars we were talking about, you typically only have a few layers, maybe hydrogen, helium, maybe carbon, or oxygen, but in more massive stars, you can end up with several layers of different elements inside the star, with the heaviest elements at the center, because those are the ones that have undergone the most fusion. Okay, and so we will talk about those more massive stars here in the next video, along with this Chandrasekhar limit and electron degeneracy. So again, as always, let me know if you have any questions, and I will see you in the next video.